Okay, chemists, in this crash course, we're going to look at topics related to thermochemistry that you might have to know for the AP exam. And I broke them down into four things: calorimetry, Hess's law, heats of formation, and bond energies. These all have to do with amounts of energy related to primarily chemical changes. Calorimetry refers to indirectly measuring the heat of some system by directly measuring the heat related to some surroundings, and knowing that the sum of those two will add up to zero. So the heat of one process is the negative of the heat of the other. And the most common thing we use for this is water, because we know a lot about water. If we change the temperature of some quantity of water, you can calculate what amount of heat that is related to how much mass there is, its specific heat, and its change in temperature. A chemical reaction will have an amount of heat that's based on how many moles of reaction there are, and then the delta H of that reaction, which we'll see a couple of examples of when we do a few problems in a moment. And then it's just a manipulation of units and summing those two together to get your heat of reaction, or whatever your unknown might be. Maybe it's to find the specific heat of substance X by indirectly measuring the heat of substance Y. So the other three that are on this crash course all have to do with getting that delta H value. How do we get that delta H value? Well, Hess's law has to do with adding reactions together with known delta H's to get the net delta H that we're looking for. Let me show you very quickly what I mean by that. So let's say I have the reaction of C2H6 plus, or actually let's have it decompose into C2H4 and a hydrogen. And then separately, I have the formation of 3 hydrogens and 2 carbons to make C2H6. And let's say I know the delta H of that first reaction, and I know the delta H of the second reaction. If I wanted to get the delta H of some other reaction that happens to be the sum of the two, that would be the C2H6's cancel, and one of the H2s will cancel. I could have a net reaction of 2 H2s plus 2 carbons to make a C2H4. Well, the delta H of this one, I'll call it delta H3, is actually just the sum of the first two. That's how Hess's law works. That's a very simple Hess's law example. Sometimes you need to manipulate the reference reaction by maybe reversing it, which means negating it, or multiplying everything by some coefficient, and then you multiply delta H by that same factor. But then you can add them together to get your net delta H. That's how Hess's law works. Heats of formation is actually very similar. It's actually an application of Hess's law, and it comes from the fact that we can use reactions that actually look like this, what are called formation reactions, where you make 1 mole of a substance from its elements in their standard state, and they have known delta H values that could be given. So if I wanted to look at, I'll look at the first one that's up there, C2H6 becomes C2H4 and an H2. These all have numerical values for their delta H of formation. This would have a formation value. This would have a formation value. And hydrogen is an element, and in its standard state, it actually would have a formation value of 0, but all the others would have something numerical. And then the delta H of this reaction is simply the products minus the reactants. I would add up all the delta H's of the products, in this case just the C2H4, multiplied by 1 because of its coefficient, and subtract everything related to the reactants, which is just this one C2H6, and that's how I get the delta H of a reaction. If I wanted to look at bond energies, I'll use this same reaction again, C2H6, but I'm actually going to draw a structure of C2H6 and show it turning into a C2H4 and a hydrogen. Here, delta H is everything that's broken minus everything that's formed, which can be very confusing because that looks like products minus, reactants minus products, which is the opposite of the previous one. That was products minus reactants. It's very easy to get these confused, but they are completely different. One is based on reference formation values. One is based on bond energies, which are tables of data that we have in all these different types of bonds. And here it would be breaking, it looks like 6 CH single bonds, 1, 2, 3, 4, 5, 6, and I'm also breaking a CC single bond. So I'd actually write 6 times a CH bond and 6 times a CC bond. And then you are forming, so subtract 4 CH single bonds. You're also forming 1 carbon-carbon double, and you're forming an HH single bond. So I would look up these numbers. They'd have to be given to me. You never need to memorize these kinds of things. Plug them into broken minus formed, and that would give me an approximation of the delta H value. So that's a rundown of the kinds of things you might see on some practice questions. Speaking of, let's look at some practice questions. So this is a multiple choice that says we mix 10 mils of 1 molar NaOH with 10 mils of 1 molar HCl in a container. It's initially at 20 Celsius, it goes up to 26. They want the delta H of the reaction, the specific heat 4.2, and the density of everything is 1.0. So this is a calorimetry question, which is Q system plus Q surroundings is equal to 0. And here our system is this chemical reaction between sodium hydroxide and HCl. I'll just write that up above. Sodium hydroxide plus HCl. And you should know, without even having to write it out, that's a 1-to-1 ratio. It makes water and salt. Net ionic would be H plus OH minus makes water. It's not even limiting. We have exactly the same amounts of each thing. You have 10 times 1 molar. You have 10 millimoles of NaOH, and you also have 10 millimoles of HCl. So that actually means I have 10 millimoles of reaction. That's what that tells me right there. And I'm going to need that because my Q values, the system's the reaction, which is N delta H. My surroundings is the temperature changing of the water, which is really the solution itself, which has a mass. So delta H is a negative MC delta T divided by N. And I look back at the question and figure out what I've got. What's my M? Careful, it's the sum of everything. This reaction becomes its own surroundings. So I add the two volumes, which are actually masses. So this is 10 grams plus 10 grams. So I get 20 grams. The specific heat they told me is 4.2. And the delta T is final of 26 minus initial of 20, so 6. What's N? N is our moles of reaction, which is based on your moles of limiting reactant, which is frankly either of those things. So it's 10 millimoles. And if I think about my units, it's obviously millimoles in the denominator. This is grams, this is joule per gram degrees Celsius, and this is degrees Celsius. So we're left with joules in the numerator. Now, most multiple choice questions you got to do without a calculator. When it's in paper and in person, that's the case. So 20 times 4.2 times 6 over 10. I'm going to do 20 divided by 10. That gives me negative 2 times 4.2 times 6 joule per millimole. Let's see, 2 times 6, I'll do negative 12 times 4.2 joule per millimole. Well, 12 times 4 is 48, plus another 12 times 0.2, that's another, it's 2.4. So I have 48 plus 2.4, this is 50.4. So this becomes negative 50.4 joule per millimole. And I look at the units, oops, they're all kilojoule per mole, but you know what, that's okay. This is a wonderful point to point out that a joule per a millimole is actually equal to a kilojoule per mole. That's very useful, so you don't have to worry about converting into and out of different metrics by factors of 1,000 and risk making a mistake. So we've actually got the answer right in front of us. They rounded to 2 sig figs, and it looks like it's A, negative 50.4. Let's look at a few other multiple choices while we've got all this fresh in our heads. So the next one says, what's the magnitude of heat released when some mass of aluminum reacts with iron oxide according to this reaction? So given a mass and a delta H and this reaction, let's get the magnitude of heat. So we have 108 grams times, this is aluminum. There's 1 mole of aluminum for every 27 grams, roughly, if you look it up in a periodic table. Looking at the reaction, there's 1 mole of reaction for every 2 moles of aluminum. I got to be careful because that coefficient of 2 goes with this value, so I need that when I'm converting my units. And then there's 850 kilojoules released. You can tell by looking at the choices they took the absolute value per mole of reaction. This is another multiple choice, so I got to do this without a calculator as well. Well, luckily 108 divided by 27, that's just 4 times a half times 850. That's 2 times 850, and that works out to be 1700. No calculator needed. Next, given the table of heats of formation, what's the delta H for methane plus 2 oxygens makes 1 CO2 and 2 waters? Heats of formation, I'm thinking products minus reactant. That's what formation makes me think of. So I have 1 CO2 and 2 waters that I need to add up as what my first term is. And if I look at the choices, that's only shown up in choice C. I need 1 CO2 and 2 waters, and then I'm subtracting 1 methane and 2 oxygens, but the oxygens have a value of 0, so I'm just subtracting 1 methane, so that's choice C. Don't worry about the math, they gave it to me as a numerical setup. Next one, given the 3 reactions, what else is needed to define delta H? This is a Hess's law. I can tell because I'm given reference reactions and I want the third one. So let's highlight what we're given and see what we're still missing. I need something related to graphite, I've got it. I need something related to C2H6, and I've got it. I need something related to H2, but I don't have that yet. So the reaction that I need has to have H2 in it. So I'm going to get rid of choice A and choice D. The other 2 have H2 in them. And then a quick scan shows me that I'm going to have reactions that also have things like other oxygens and water molecules that I can get rid of. So frankly, it makes sense that I would have a reaction with oxygen and water in it. So choice C makes the most amount of sense in a hurry, and if you map it out, you'll actually work out that you can manipulate the first, second, and choice C to get a delta H value that's unknown. They're not even having us calculate it, they just want us to know, what do we need? I could see a part 2 to this question, or just a follow-up multiple choice where we actually get the actual value, or at least the numerical setup. Okay, one more multiple choice. This is a lab-based question, and here's an example of the only place you should really look out for sig figs. It's almost always with temperature changes, delta T's, and given a lab setup. Delta T is always final minus initial. So if I look at the chart, or the picture, this looks like it's right on the line at 20, but remember how sig figs work. You look at how it's graduated. This is marked off every 1, 21, 22, 23. So we can always write it to the decimal place that we have, which would be the ones place, and then 1 more. So we're going to have a number that's to the 10ths place using this thermometer. That's the best way to approximate given a scale like this. So I'm going to write down 20.0 for this final temperature. What was the initial temperature? Well, it looks like it was more than 25, but less than 26. So I'm going to write down 25 point something. I don't even care what it is, because I can tell from the choices, it's just how many sig figs I want. So when I subtract 20.0 minus 25 point something, I'm going to get something to the 10ths place. No less, no more. Choice C looks like the right answer. That's the one I'll circle. This is really just a testing of how precise the thermometers are. Okay, let's finish up by looking at a free response question, also related to thermochemistry. Here they give us a reaction and they want Lewis structures for the 4 molecules involved. So if I draw a methane molecule, that's a carbon, with 4 singly bonded hydrogens attached. For generic Lewis structure, you don't need to show the shape. It happens to be tetrahedral, but they just want to see that you know the right bonding. Fluorine has a whole lot of lone pairs on it. I don't know how picky they would be about putting them in, but I guarantee it's not wrong to put them in, so I'm going to do that. CH3F, what's called fluoromethane, has 3 CH single bonds and 1 fluorine attached to that carbon. And then we have a molecule of HF. And I can tell I'm already gearing up for what they're going to have me do next. They want me to get the delta H given the bond energies, also called the bond enthalpies. So delta H is going to be the broken minus formed. So this is the opposite of heats of formation. It's the reactants minus the products. And what am I breaking? I'm breaking 4 CH bonds. I am also breaking an FF bond. I am forming 3 CH bonds, and I am forming a CF bond, and I'm forming an HF bond. And I can actually cancel some of these out already, because I'm breaking 4 CHs but forming 3, so that's a net of just breaking 1 CH bond. So when I have to do the math, which for a short answer question I gotta do it, I use all these values just once. So 413 plus 155 minus 485 and then minus 567. And you could do this without a calculator. It's actually not too bad, because if you look at the first 2, that adds up to 568, which is just 1 more than what we're subtracting. So 568 minus 485 is going to give me negative 484. Most free response questions you can do with a calculator, but this one we could just do a self-check. I'm going to put in my units. It's going to be kilojoules per mole of reaction, meaning how it's formed. And then the last thing for today, on the diagram below, fill in the expected curve to show the progress of this reaction if it were to occur in a single step. So a single step has 1 transition state, and we just calculated a negative delta H, so my products are going to be lower in energy. That's where CH3 F and HF will exist, and all I should have to show is that you hit some activation energy and then come back down to your product energy. Just as a follow-up, remember there's your activation energy, they didn't ask for it. If this was endothermic, it would have some activation energy and then end higher. The transition state is always going to be the highest point on your graph. And if it was a catalyst, then you would have a multi-step process that would actually have 2 activation energies, but you would start and end at the same spot. So that wraps up a review of some practice questions related to thermochemistry and the kinds of things you might need to know. Thanks for watching.